Hello everyone, thank you for attending this presentation. My name is Shaolun Ruan, and I'm a PhD student at Singapore Management University. In this video, I will present our recent work, Venus, a geometrical representation for quantum state visualization. The agenda of this presentation is as follows. So now let's start with the introduction of the background. We all know that quantum computing has experienced impressive growth in recent years, with a multitude of applications demonstrating quantum speedups in areas such as optimization problems, machine learning, cryptography, and finance. The past decade has seen the emergence of real quantum computers from various quantum vendors, including IBM, Rigetti, Honeywell, and NQ. What sets quantum computing apart from classical computing are two fundamental properties: quantum superposition and quantum entanglement. These properties are the real power and advantages of quantum computing. Quantum superposition refers to the unknown quantum states before they are mirrored. After mirroring a qubit, it collapses into either state 0 or 1 based on the deterministic probabilities of all possible states. For example, if the probability of mirroring a result of 0 is 0.5, the probability of mirroring a result of 1 can be also 0.5. Quantum entanglement, on the other hand, facilitates correlations between multiple single qubits. When qubits are entangled, manipulating one qubit can directly impact the state of the other qubits. Two-qubit entanglement is particularly crucial in many popular applications, especially during the near-term noisy intermediate-scale quantum era, where the number of qubits is limited. So it is important to visualize the quantum states, which can improve the interpretability of quantum circuits and enhance the user's confidence in the quantum program. Specifically, quantum computing first needs to visualize the quantum states with more than one qubit. Considering that the two-qubit entanglement state is a specific type of two-qubit state, the representation of two-qubit states remains underexplored to quantum computing researchers and developers because the two-qubit state does not simply accumulate multiple single qubit states. Moreover, to make the mirrored probability easier to understand, the visualization should provide users with an intuitive display and then the explanation of the probability, making the users aware of the rationale for a certain mirrored probability. For example, let's say the probability of state 0 is 0.5. So how can we understand this value? So the Bloch Sphere, a widely used visualization technique, was proposed to address this requirement. As shown in this slide, the Bloch Sphere employs a point on the unit sphere to represent the amplitudes of a pure single qubit state. However, despite its prevalence, several issues still exist when utilizing the Bloch Sphere. First, the Bloch Sphere cannot visualize quantum states with more than one qubit. When two qubits become entangled, the Bloch Sphere's visualization method fails, because the quantum states cannot be reduced to three dimensions in the same manner. Second, while the Bloch Sphere can represent quantum states, it does not provide any intuitive display of the probability of all basic states, let alone explaining the probability to enhance the interpretability of quantum states. But probability is a fundamental characteristic of quantum states because it directly reflects the quantum superposition. Third, three-dimensional visualizations such as the Bloch Sphere have been demonstrated to underperform their two-dimensional counterparts in terms of the precise measurements. Previous research has discovered that the three-dimension visualization of the Bloch Sphere introduces the potential for visual occlusion, resulting in inaccurate observations for quantum states. To this end, we collaborate closely with 5 domain experts in the field of quantum computing. Through a co-design process, we iteratively collect design requirements for observing quantum states, which in turn inform our subsequent visual design. And the collected design requirements are shown here. So in order to meet the aforementioned requirements, we introduced Venus, a novel visual design for quantum state visualization. Venus supports the representation of quantum states for both single qubit and two qubit states, thus serving as a foundation for two qubit entanglement representation. Furthermore, Venus enables users to understand the measure probability through the visually correlated geometrical shapes, making the interpretability more effective and smoother. So let's first take a look at the basic concept in quantum computing for the subsequent content. A single qubit state can be represented as the equation 1, which including two states, state 0 and state 1. The coefficients before the states are called the amplitudes, which are the complex numbers. Let's say A is the real part and B is the imaginary part for the amplitude alpha. So the probability of measuring state 0 is the sum of squares of A and B. And we all know that the sum of the probability of all states must be 100%. So the A, B, C, and D satisfy the equation 4. The sum of the square of them equals to 1. So the two qubit state is similar with a single qubit state, where we have four states 0, 0, 0, 1, 1, 0, and 1, 1. The calculation for amplitudes and the measure probability remains unchanged. So the normalization constraint has 8 values as shown in equation 4. So now I will introduce the detailed visual designs. First, I will start from the representation of the single qubit, and then I will introduce the two qubit representation extending from the single qubit. The single qubit version of Venus is shown here. It visualizes, for example, the quantum state of phi shown on the bottom. Venus mainly consists of two coordinated visual elements, a collection of right triangles employed to visualize state vectors and circumscribed semicircles of these right triangles, which explicitly convey the probability distribution associated with the corresponding quantum states. First, to represent the state vectors, we use blue and red triangles to indicate the two amplitudes, alpha and beta, of the state vectors respectively. We encode the absolute values of real parts, that is A and C, and the imaginary parts, that is B and D, of each amplitude by the line segments in black and gray, respectively. We also apply the double lines to reflect the negative real and imaginary values. And then, to visualize the measured probability, we use the area of the semicircle circumscribed by the red triangles. We already know that the probability is the sum of squares, let's say A and B. At the same time, the area of the semicircle can be calculated by equation 9. So the area of the semicircle is proportional to the probability of the quantum state. We then can observe the relationship between the two probabilities via the comparison of the semicircle area. At the same time, we can directly find out that how the amplitudes affect the probability by observing how the semicircle area is affected by its circumscribed right triangle inside. So the users can achieve mathematical intuitiveness about the probabilities determination. Furthermore, we can also encode the normalization constraint into the visual design. Based on the equation, the baseline of the white triangle will always be 1. This can enhance the confidence in the validity of the amplitudes of the quantum states via this baseline. So, extended from the single qubit, the two-qubit visualization of the quantum state is similar. In this scenario, the design has 4 amplitudes and thus 8 light segments to represent the state vectors. Also, the probabilities of 4 basis states, that is 0, 0, 0, 1, 1, 0, and 1, 1, can be represented by the areas of the 4 semicircles. Moreover, based on the equation, the visual design can also reflect the normalization constraint by the baseline with a fixed length of 1. So now I will briefly demonstrate our visual design Venus using an example, which is a quantum classifier based on two-featured iris dataset. The circuit shown in this slide is an implementation of the quantum classifier. We firstly randomly select a data point whose label is 1 out of the set 0 and 1. We expect to see when the semicircle on the right will be larger than the left one, and how this state vector affects this convergence process. We evenly output the results of the data points quantum states to see the evolution of the quantum classifier. A1 to A4 depict the epoch 1, 25, 50, and 100 respectively. We can easily identify from A1 that the probability of label 0 is significantly larger than that of label 1, indicated by the area of the respective semicircle. It shows the initial state of the data point and the model at the beginning stage of the training. After epoch 25 in figure A2, the area of the semicircles which indicates the probability of state 0 and 1 are almost the same. And we can see that this is because of the decrease of the imaginary part of the amplitude for state 0. And then the semicircle of state 1 is significantly larger than that of state 0 and epoch 50, and almost remains the same at epoch 100. From the above findings, it is obvious that the quantum classifier has converged around epoch 50 for this data point. So we can apparently observe how the probability was affected by the evolution of the state vectors indicated by the light segments within the semicircles. Also, these findings provide us with good guidelines for model tuning. For example, during the parameter initialization for the rotation gates, we can choose those rotation angles which could make the absolute value of real parts larger than the imaginary parts for both state 0 and 1, because the increase of the real part in state 1 mainly results in the larger area of the red semicircle from figure 1.4. At last, we also conducted in-depth expert interviews with 14 domain experts to evaluate the performance of Venus for given tasks. We also invited every participant to rate the Venus using a 7-Likert scale. Detailed ratings and questionnaire example are shown in this slide. So our evaluation shows that Venus can effectively facilitate quantum state visualization. However, there is still some feature work. First, the update of Venus is driven by the input number of amplitudes, which requires users to input the real and imaginary parts of amplitudes manually. Participants reported that this is kind of inconvenient to type in the amplitude values every time. We will make this process smoother, let's say automatically extracting the values of the vectors on the screen. And second, compared with Bloch Sphere, it can effectively visualize the quantum state with 2 qubits. However, we are still exploring the methods to support qubits more than two to fit into more general scenarios in quantum computing. To sum up, we already introduced the visual design and the usage of VNS, which is a visualization approach for visualizing quantum state representation. Based on the visualization of the state vectors, we uh, implemented multiple coordinated 2D geometrical shapes to explain the measured probability distribution of all basis states. Moreover, we employ the same visualization methods to allow the VNS to support the representations of single qubit and also the two qubit states. So that's all for the presentation of our paper. And if you have any questions or suggestions, please feel free to contact me via the email below. And my personal homepage and QR code are shown here. So thank you for your attention, and I'm open to any questions.